welcome to this new blog. Today I will introduce a new model, convolutional neural network, CNNs, and I will use a very famous dataset in computational vision. This is Mnist, and in this dataset, the task is handwritten digital recognition, and the input is um, the handwritten digital images, and we give this image to the CNN, and we want to predict what the corresponding number it is. And this is an example of our input data. We have an image and some corresponding labels 0, 1, 2, 3, 4, 5 to 9. And let's move on. So first we should import some necessary Python libraries like Torch and Torch Vision. The Torch Vision, because this is a computational vision task, so we need to import this one. Then we set the seeds. So the seeds will help us to reproduce our result. Now same thing, we set the device. I'm using the Colx, so the device on my notebook will be GPU, and then I will add something to process the input data. So because it's image, we need transform to process and prepare the Mnist dataset for us. So in this function, we need two elements. First is two tensor. So we should convert the input image data to tensor, and then we normalize the data. Because our input data is 2D, two-dimensional input, so we should normalize two-dimensional. So here we will use this normalize function to normalize the two-dimensional input. Okay, then we will use this dataset function because the Mnist is a built-in dataset in PyTorch, so we can directly use the datasets.mnist to download the data, and the dataset will save in the image data directory, and I put it in my root directory, but you can give different directory here. And I download the training set and the validation set, then load this dataset to the data loader to generate the batch. And we set the batch size to be 64, and then we load this dataset. Okay, then we go to explore the dataset. First, we will extract the first batch as the example to see what's in the dataset. And in this dataset, we include two components. First is image, our input. Second is label. Label is our target, right? And you can see when I print out these two elements, the first element, image, has these dimensions. So first is 64, then 1, then 28 by 28. For the label, we have 64 dimensions. So let's see what this means. First, the shape of the image is 64 by 1 by 28 by 28, which suggests there are 64 images in each batch, the batch size, and in each image it's one channel. So because our image is black-white picture, so we only have one channel. And if you have a colorful image, you will have three more channels. It's RGB, right? So and in each channel, we will have the 28 by 28 pixels. So this is our image size, 28 by 28. And for label, the batch size is 64. So it suggests there are 64 labels in the image. Okay, so let's display the first image from the training set. We use this plot, MATLAB plot, to show you the image. So because this is black and white image, so we use a grayscale to show an image. You can see we have 28 pixels, then these pixels form this image. And this looks like some number, I guess it's 4 or 9. Okay, and let's see all the batches. So this is the first batch. We have 64 image in this batch, and each one has is a handwritten digit, and we should have a label corresponding to this digit. Okay, so let's move to the CNN. So the CNN is a neural network, a deep learning neural network. So in this architecture, we have many elements. So first element is the input layer. That's our input image. That is a convolutional layer. After that, we have pooling layer. Some will also call it as the downsampling layer. Then we have the fully connected layer and output layer. So let's move to the first element of convolutional neural network. So definitely the most important thing, the essential thing is the convolutional layer. The convolution is essentially a moving kernel across the image being studied. So let's look at this example. So our input is this 5 by 5 matrix, and our kernel, our filter is 2 by 2 square, and you can see we assumed here, so our kernel is k. Okay, and this k, we assume all the weight of k equal to 0.5. So this is, it's 2 by 2, it's 4 element, all are 0.5. Okay, so let's do the first calculation. The first calculation gives the blue square. This blue square, we have 4 element, which is 2, 3, 2, 1.5, and we multiply those this element, do the dot product with the k, the weight matrix k, our filter k, 0.5, 0.5, 0.5, and 0.5. We do the dot product and we get the result. This is a calculation, and we get to the result is 4.25. Okay, uh, and in this convolutional layer, our stride is once each time we move one step. Okay, so we move one step to second square this blue square, and we extract the element in this square is 3, 0, 1.5, 2.5 by the k, and our result is 2.5. Okay, uh, and we keep move this square to get the uh, convolved output on this convolutional layer. So this is convolutional layer. Uh, and we want to say you can also use multiple convolutional kernel, so to convolve the input tensor. And um, the weight of k can be trained. We can use backpropagation to uh, uh, update the weight of the k, and um, this k will help us to extract different information in the input. The second element is ReLU. So ReLU is the nonlinear function. So we already know it. The ReLU will convert all the negative value to 0 and keep the positive value as it is. Okay, and the third element is pooling layer. So we also call it as downsampling layer. Okay, and in this layer we use the max pooling here, and you can also use the min pooling or the minimum pooling. And in this layer, we just directly select the max number in each kernel. Here we have a kernel which size is 2, is 2 by 2. So in first step, it's a blue square. In the square, we extract 4 element 2, 3, 2, 1.5 here. Then we just directly extract the highest number to our output, which is 3. And the same we move our stride here is 2, so each step we move 2 element. We move to here. So in this there are no overlap here, right? So we get a new highest number here, which is 5, and put 5 to our output square, then move to next one. But the next one here, we are at the boundary. We don't have, in the original matrix, we don't have more element to put into the kernel, so we use the pad to handle the boundary problem. The pad will be 0, so when we do the max pooling, we will select 7 as a new input, new output in our max pooling output. Okay. After that, the fourth thing is fully connected layer. It's we already know it, and we already use it. We know we give some matrix, then the fully connected layer will return some matrix in different dimension. and then is dropout. Dropout will help us to deal with the overfitting problem in our model. Uh, okay, so let's go to build a network. So in this work, we will use a 2D convolutional unit. We will have 2D convolutional unit, and in each unit, we should have this element, this submodules, convolutional layer, ReLU, uh, and the pooling layer, and they are sequentially, we pass the information to this layer sequentially, and we follow, then it will follow with a sigmoid layer and a fully connected layer. Okay, and let me give you a big picture overview of this network. So this example from the Ryerson University, and this is the visualization of a model. For example, here I give you a number 7, and the first part, this is our input. This black block, it's black background, and our number is blue here. Okay, this is our input. So here we extract the first batch as our input, and the input image dimension is 64 by 1 by 28 by 28, and the label size is 68. Okay, so that's because our input is each image is two-dimensional tensor, so we will use the 2D convolutional layer here. You can go to this PyTorch document to learn more about the 2D convolutional layer and see what's the hyperparameters in this module. And let's move to the first layer. So in this model, this is first layer, the convolutional layer 1. Here they use a different number of filter, but because I guess it's easier to visualize, but here we will use different number. So the let's see, in our example, in this function, the convolutional 2D layer, we should specify some hyperparameters. So first hyperparameter is in channel. So our input channel is 1, right? So the in channel number of in channel is 1. Second is out channels. So out channels is a number of channel of the output tensor. You can also consider how many kernels we will apply, we will use in this convolutional layer. And each kernel will help us get a different part of information. Okay, and so here we set the input channel equal to 1, and here we assume our output channel should be 32. So here we set the output channel to be 32, and the kernel size is argument is the size of the convolutional kernels. So we want to know how big is our kernel. So in previous example, the kernel size is 2 by 2, right? Here, the kernel size, we want to get the 5 by 5 kernel size. So here we use a kernel size equal to 5. If you only give one number, the kernel size will be it will be a square kernel, and its size will be 5 by 5. But if you want to get a different shape, you can mm, you can you can use a tuple here. You can use height size first, then the width size in second, um, in the tuple. Okay, and the third thing is the stride. So the stride controls the stride of the cross correlation. So here we use the stride 1. So each step we only move one item. Okay. Finally, we should define the padding. So the padding, you already know the padding. This is padding to handle the boundary problem. So, but we should know what's this number we should put here, right? Basically, we can use this formula to calculate the output size of any dimension. So here, and you can use this formula to calculate the output for convolutional layer or the pruning layer. Okay, so here in this formula we have many parameters. First, let's see this function. So first is WIN. So WIN it's the uh, width or height of the input. In our case, our WIN, no matter the width or height, they're same. It's 28. Okay, and K is a kernel size. Kernel size equal to 5. Here we use 5 by 5, so it's 5. And for P, so P is our target. We want to know what's the P, the padding number we want to get. So we have a question on P, and it's S. Okay, S is the stride. So our stride is 1. And in our case, we have the weights of the output. So here we mentioned we wish the keep our input and output dimensions the same. So here it's also equal to 28. And you put those together, then use this formula to do the calculation. You will know you need the padding. You need 2 paddings here. So this padding equal to 2. Then we instantiate, we initialize the convolutional layer, then give the image input to convolutional layer, then output will be 64 by 32, our number of channel, and we will not change the image dimension, so it's still be 28 by 28. So in this case, we pass the input, this input, to a convolutional layer, and this is output of convolutional layer. They use the filter 2, but this is filter number, I see. So yeah, we will have in this output we will have 33 output in this layer, and this is we will get the output come from the 32 different filters. Okay, and let's move to the ReLU layer. So after that, we will use a ReLU on top of the output of a convolutional layer. So as you know, the ReLU will not change the dimension of the input, so we just give the convolutional output to the ReLU, then ReLU will give us the same dimension output. Okay, so after that we will have a new layer. So the output of the ReLU will um, send to the max pooling layer. So here they called it as the downsampling layer. So this is downsampling layer. Our downsampling layer is max pooling layer, and here we use this function from PyTorch. Exam, you can go to the document, see how it look like, and learn some hyperparameters, how to manipulate them. Okay, so let's move to the code. So when you instantiate the max pooling layer, you should provide some hyperparameters. The kernel size here, we want the kernel size is 2. Same, what is kernel size? You can see it's window size, kernel size. So it's how large of this square. Here is 2, right? So our kernel size will set to be 2. Okay, and stride, the step size here is 2. Each time we'll move 2 elements. Then because here we mentioned we want the output dimension will be the half of the input dimensions in order to reduce the dimensions. So here we will set the pooling equal to 0. Yeah, because when you use a formula, you can know in this case WIN equal to 28 and WOUT equal to 14, half of it, half of the input, and stride equal to 2, and the kernel size equal to 2, and you will know the p should equal to 0. Okay, and after that you instantiate the pooling layer, apply the pooling layer on the ReLU output, then we'll get a new output. This output is 64 batch size, 32. We will not the pooling layer will not change the number of channel, so it will same 38, 32. Then 14 by 14. We halved the image dimension. So in visualization, it's this layer. No. Okay, it's here. It's downsampling layer 1, and it's much small. You can see the dimension already smaller than the output of convolutional layer. And okay, so let's move to the second 2D convolutional unit. So we already finished the first layer, second layer, this is, and the downsampling layer. This all will be the first unit, the convolutional unit. Then we'll move to the second convolutional unit. First, same. The output of the first convolutional unit, the max pooling output, will be the input of the second convolutional unit. Okay, so here first we will have a convolutional layer. we will create a convolutional layer and set the input channel is 32, and 32 equal to the input channel equal to 32, and we assume here the output channel will be 64, so this number be 64, and the kernel size same as before. We use 5 by 5 kernels, stride be 1, pad equal to 2. We use this calculation, this formula, we can know the pad size should be 2. Okay. After that, we use a ReLU function, get the ReLU output. Then here, use the same logic. We use ReLU output as input, and we give this to the 2D max pooling layer. We want to continue reduce the size, so we want the output dimension should be half of the input dimension, and the kernel size we will use 2 by 2, and so the kernel argument equal to 2, the stride equal to 2, and same, we don't need pad here, so we apply this second max pooling layer, and now we get the max pooling output. So here, this layer is second convolution layer, and this one is a second downsampling layer. Okay, so you can see it's already changed like the different changes to different component. So let's move to this one, this two linear layer. So you can see our output, the output of the convolutional unit is a 4-dimensional tensor, right? So which is this number, right? The 64 by 64 by 7 by 7, right? And here, first we should flatten the 2D tensor and flatten it to flatten the 4D tensor to a 2D tensor, because we should match the input size of the fully connected layer, which should be batch size by feature size. And here our batch size is 64, and the feature size, because we'll flatten the last three dimensions, so the feature size will be 64 by 7 by 7, which is 3136, and you can see this is the flattened layer here. Okay, this is fully connected layer. Okay, and we use a view function to flatten the output, and we get this flattened output, which is 64 by 3136. Okay, and before we give this tensor to the linear layer, we will use a dropout layer to avoid the overfitting in the model. Here we use a dropout layer which dropout rate is 0.5, then we use it on top of the flat output, then get the dropout output. And after that, we will use it on a sigmoid linear layer, and this is a fully connected layer. So it's same. We instantiate a linear layer which input dimension, the input feature number is 7 by 7 by 64, this number. And here we want to map these features to 1000 features. So we set second parameter to be 1000. Then we use this function to process dropout output. Then we use a sigmoid function and to add this nonlinearity on the linear layer. Then we print out the output from the first linear layer. We get the 64 by 1000, and this output will send to the second linear layer. So here we will send to a second linear layer here, right? And this is we already get this output, this 1000 layer, 1000 unit here in our model. Then we will send to a prediction layer. Okay, and the last one, the second layer is prediction layer. So in this layer, the output will give the prediction probabilities across the labels. So in this layer, our input is 1000 dimension, and our output is 10 because our prediction target is this numbers 1, 2, 3, 4, 5 to 9. So here it predicts 7, right? Here we will get the output from the last linear layer. Then we use a cross-validation loss function to calculate the loss of this module. We give the prediction output and the true label to get the loss here. Okay, so we introduce CNN step by step. So now we will give a we will put everything together and create a CNN class here. So I want to introduce advanced function in the PyTorch, which is sequential layer objects. And you can see within the class initial function, you can use a sequential layer objects. It's a sequential container, and the module will add to it in order they are passed in the constructor. So you can visit the document and see more information about the sequential layer objects. So this is our sequential layer, and we put our different submodule in this sequential layer. So actually our sequential layer is our convolutional unit, right? So it actually will help us to organize our code. And in this function, we should include 3 element convolutional layer, value layer, pooling layer, and they are sequentially process the information. And here, this is our first sequential layer. We have 3 elements: 2D convolutional layer, value, max pooling, 2D max pooling. The second convolutional unit also have the convolutional layer, value, max pooling. After that, we need the dropout linear layer, which input is this number and 1000, and this one from 1000 to 10 to predict the label. Then we build our computational graph. We put everything to the forward. So it's computational layer 1, the convolutional layer 1, convolutional layer 2. Then we reshape. You can also use a view to reshape, to flatten the 2D tensor to a 4D tensor to 2D tensor. Then apply a dropout, sigmoid layer, and the linear layer, the prediction linear layer. Then here we go to the training. The training process, we instantiate the entity and send to device, set the learning rate, our loss function, and optimizer. We use Adam optimizer. Then we use our simple method to instantiate the weight. So we will use a normal distribution to instantiate the model weight. Then we calculate how many parameters in our model. Then we train the model. Here is a training function, evaluation function. After that, we do the training. So we train for 5 epochs, and we'll print out the training loss, validation loss, and the validation accuracy, and the validation F-score. And you can see our model, the CNN model, is super powerful. You can see it can reach 99% validation accuracy and 99% validation F-score. Okay, so this is a website I'm using to demonstrate the process of CNN. You can visit this website to play with the model. Okay, thank you very much. And this is a tutorial about use CNN. So because CNN originally created for the computational vision task, so I just want to use this task to introduce CNN. And then I will introduce CNN, some application of CNN on natural language processing, and it's made more related to our work. Okay, see you soon.